Welcome, I'm Jianying Dong, Assistant Professor in the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. The topic of this lecture is the control of electrical drives in EVs. The learning objectives of this lecture are as follows. First, we will learn how to analyze the dynamics of an electric drive. Second, we will study the concept of closed loop or feedback control. Third, we will investigate how the controller is implemented in electrical drives. After that, we will dive into the hardware architecture of motor control and go through critical hardware components. Let's first take a look at what an electrical drive is. An electrical drive is a system that controls the motion of electrical machines, including the power electronics, the electrical machine itself, various sensors, and a controller. The figure below shows the architecture of an electric drive in the EV. The inverter is connected to the battery at one end and to the electrical machine at the other end. A field-oriented controller controls the gate signals for the inverter. Here, field-oriented control means the controller tracks the direction of the magnetic field and sets the voltage command to reach the required torque accordingly. Let's first look into the dynamics of AC machines. As discussed in previous lectures, to simplify our analysis, it is advantageous to convert the three-phase machine to its two-phase equivalence by transforming the variables from the state-based reference frame to the rotor-based rotational reference frame. As we can see in the animation, the three-phase currents are sinusoidal and displaced by 120 degrees, or in 2 pi over 3 radians in phase. The three-phase current will create a rotating magnetic field in the electrical machine. Then, we can make an equivalent two-phase machine by replacing the three-phase winding with the equivalent two-phase winding, alpha and beta. As we can see, to create the same vector rotating in space, the two-phase currents should be displaced by 90 degrees in phase. In the state-based equivalent two-phase system, the currents are still time-varying. If we define a new reference frame, dq, rotating together with the magnetic field, the vector formed by the currents will rotate synchronously with the dq reference frame. Then, the current dq components become constants. When the d-axis of the rotating reference frame is aligned to the axis of the magnetic field, it is also called magnetic axis. Then the q-axis becomes the torque axis. Let's continue our discussion on the dynamics of AC machines concerning differential equations. Modeling in the UVW system can be very complicated. First, there are more variables for a three-phase system compared to a two-phase system. The three-phase system has rotor position-dependent inductances since the inductances depend on the air gap between rotor and stator. Moreover, there are cross-coupling of parameters along the three phases, for example, the mutual inductances between the phases. When the machine is transformed to its dq reference frame-based equivalence, the equations and variables are significantly reduced, as we have already seen in the previous lecture. Moreover, there is no cross-coupling of parameters because d and q axes are orthogonal. Therefore, the magnetic field and the torque can be regulated independently. The best way to understand these equations is through a block diagram. We have two axes, d and q. Each axis has its own flux linkage and voltage equation. The dot above the variable denotes its first-order time differential form. The simulation block model is designed using these variables in vector form. If you start by looking at the left, the UVW three-phase voltage is converted into its stationary two-phase alpha beta equivalence. Then, the flux linkage in alpha beta is derived by taking the integral of the voltage. Then it's transformed to the dq equivalence with the rotor position information. Then current in the dq reference frame is obtained by applying the flux linkage equation. The torque can then be calculated from the dq flux linkages and dq currents. If we look at the motion equation, we can see how mechanical rotor speed is calculated from machine output torque T and load torque TL. Similarly, the rotor angle can be calculated by integrating the speed variable. The transformation blocks require the electrical position of the rotor during transformation, which is achieved by applying pole pairs to the mechanical rotor position angle. To control the output of an electrical machine, a closed loop or feedback control of torque is needed. In EVs, the control objective is to supply the correct three-phase voltage to produce the right torque to attain the required speed. At first, the torque command is translated to dq current references in the controller. Then the reference currents and the measured currents are fed to the current controller to generate a suitable dq voltage command. The voltage command is then fed to the inverter through a pulse width modulator, where get pulses for the inverter are produced realize the voltage command. The current controller can be a proportional integral controller or a PI controller for short, as is implemented in the block diagram on the bottom. The proportional and the integral constant Kp and Ki of the PI controller is tuned to achieve the satisfied dynamics of the electrical machine. Electric drive hardware architecture involves an inverter consisting of power electronics and gate drivers, which has already been discussed in the previous lecture. It also involves a DC bus voltage sensor, which measures DC bus voltage to calculate the right duty cycle for the gate driver. It is situated between the DC bus and the inverter. The phase current sensor placed between the inverter and the electrical machine measures the phase current for feedback control. The rotor position sensor placed near the rotor measures the rotor speed and its position for the reference frame transformations. The control hardware can be either a digital signal processor DSP or an field programmable gate array FPGA. It needs to facilitate several functionalities, including pulse width modulation, PWM, analog to digital conversion ADC, or for voltage and current sensors, and a digital encoder or resolver interface to measure the rotor speed and position. Let's take a look at the voltage sensing hardware. The voltage is typically sensed through a voltage divider with a larger resistance, which turns high voltage into small signal. An isolation amplifier is used to isolate the low voltage control circuit from the high voltage power circuit. The low voltage signal is then fed to ADC. Below, you can see an example of a voltage sensor with the description of each pin. The current sensing can be done in two ways. The first one is shunt resistor sensing. As you can see in the picture, a shunt resistor is placed in line in each phase. The shunt resistor is a small but precise inline resistor to measure the current while the voltage drop on it. The drawbacks of using this sensing technique are as follows. First, an isolation amplifier is needed to isolate the high voltage from a small signal. And second, introducing resistance in the power circuits increases the losses. However, it provides immunity to magnetic interference. That is to say, the measurement values are not hindered by magnetic fields. And it has high accuracy with the actual advantage of being very small in size. The second current sensing technique is based on the Hall effect. As we can see in the figure on the right, that the Hall module is not physically connected to the main circuit. Here, the voltage induced in the sensor VH is proportional to the magnetic effect caused by the current in the main circuit. The drawbacks of these sensors include vulnerability to magnetic interference, and cost-wise, they are more expensive as compared to shunt resistors. However, since no physical contact is there with the main circuit, no isolation amplifier is required, and the absence of any resistance means there is no power dissipation in the main circuit introduced by sensing. There are many types of rotor position sensors. We will discuss the two widely used rotor position sensors. The first one is the variable reluctance resolver. It consists of one excitation winding and two orthogonal sensing windings, sine and cosine. All three windings are wound around the stator-teeth. When the excitation winding is powered with high-frequency signal, as the reluctance changes as rotor rotates, the induced voltage amplitude in the sine and cosine windings will change accordingly. The sine winding voltage envelope follows a sinusoidal pattern, while the cosine winding follows a cosine pattern. The position of the rotor can be determined by the combination of the two voltage waveforms. The second example is a magnetoresistive sensor. It works on the principle of the magnetoresistivity effect, in which the resistance changes according to the change in the magnetic field around the sensor. Therefore, magnetic poles should be attached to the rotor in order for it to work. It has a low system cost, but is sensitive to mechanical tolerance. There are also other types of sensors consisting of a brushless resolver, which has the excitation winding on the rotor and is excited in the principle of a rotating transformer. Inductive position sensor based on the eddy current, and the Hall effect sensors. That is all about the control of electric drive. In the next lecture, we will look into the losses in powertrain of the electrical vehicle.